here you get as good a result as much thought you put into choosing the configurations. So that's a bit of a challenge, and therefore it's always good to have some recipes of how to do that. And one recipe of choosing those configurations or determinants is called complete active space SCF. That stands for complete active space, and then SCF. Now what you do here, you from all your orbitals, molecular orbitals, and let's assume again that we have a nicely, so here's sort of some kind of energies, orbital energies, and we have a nicely behaving system where you have sort of a gap in the orbitals between the occupied, what would be occupied in Hartree-Fock and virtual orbitals. What you do, you choose what is called an active space, which means you choose some set of orbitals which are important, relevant for the system here. So you choose sort of, okay, let's for example choose those orbitals, and that's my active space. Now if we sort of look at the result of Hartree-Fock calculation, then you would have those orbitals occupied and the other one empty. So you choose your active space, and that's where then sort of the art comes in, or the knowledge comes in, the understanding of the system comes in order to choose that. And then what this complete active space means, that it actually makes what corresponds to a full CI calculation in that active space. It generates all the configurations or determinants which you get by distributing those, here in this case 4 electrons, over those orbitals, over all those orbitals. And so it's a full CI in the active space. And there actually goes sort of a notation with that. You can write that up with this, where you write here how many electrons you have in the active space. So in my example, that would be 4 electrons, for example. And then you write how many orbitals you have included in active space. And that, of course, was a bit, let's make it a bit more interesting example. Let's take 5 orbitals in the active space. So that's the number of orbitals in the active space. So that would be a 4 in 5 CASSCF calculation, for example. Now that, of course, is not solving the problem that you have to choose. It's sort of just transferring to something else. Here we had to choose which determinants. Now we have to choose which are the active orbitals. And by choosing how many of the occupied orbitals you include, you of course choose how many electrons you have included. So you have to choose this active space. And even worse, you have to do that manually. You have actively to say, I want to have that and then that. So the active orbitals have to be selected. Well, and there's of course also a cost issue again, because I mean you're doing a full CI in that active space, and that means you can't make that arbitrarily large if you ever want to get a result. So it's sort of you would like to make it as large as possible. In particular, the larger it is, the less you have to think. On the other hand, you can't afford that probably, so it's a balance between them. And that means In the first place, you should include the orbitals which are important for the system you're treating. Only the important orbitals. And that could be important, for example, if you're looking at bond breaking situation, then the orbitals which describe that bond. Important for bond breaking, if that's what you're looking at. In general, the ones which go into the degenerate configurations. So for the degeneracy, remember that beryllium example, which I talk where you would have the ground state configuration. The symbols would be 1s doubly occupied, 2s doubly occupied, but there is another one which is very close in energy, which looks like this. And then obviously here I would include the 2s and the 2p orbitals in my active space. Those are the two ones which are responsible for the degeneracy, so let's include those. Or more general and therefore less specific, the orbitals which are important for the chemistry of your problem. Now what you typically start off with, at least for a system where you can do that, typical start would be all the valence orbitals. And that's also what you do here, actually. So if you're going to look at water this afternoon, so the valence orbitals would be, you take the 2s and 2p of oxygen and the 1s on hydrogen. Now, talking about valence orbitals in molecules and then talking about atomic orbitals, of course, requires that you have to figure out which molecular orbitals are formed by those atomic orbitals. If you look at a system like benzene, there you also could, if you think about valence orbitals, you could say, okay, that's of course going to be the pi orbitals, pi molecular orbitals, and that's much easier to find then. But if you don't have pi orbitals, you only have sigma bonds, then you have to sort of think a bit and look which molecular orbitals are actually the ones which are mainly formed from the valence orbitals which I wanna include. So you start with valence orbitals, but you see, I mean, in order to have a meaningful active space, you need not only occupied orbitals, you need some virtual orbitals, you need some empty orbitals. I mean, you can't get extra determinants if all the orbitals which you include are doubly occupied. Then you're ending up with one determinant, and that's not very useful. So you have to have some virtual orbitals, and you want to have enough of them. So I would say a minimal meaningful active space would be that you have, for each occupied orbital, you have a corresponding empty orbital. That's also very much in that idea. If you think about bond breaking, then you would have the bonding and the anti-bonding orbital for that bond. Remember the hydrogen example from Tuesday? In order to get the dissociation limit correct, we had to include not only a configuration with the bonding sigma G orbital doubly occupied, we also needed a configuration with the sigma U orbital doubly occupied. That's the anti-bonding orbital. If I included both of them in my wave function, I could describe the dissociation correctly. So the bonding and the anti-bonding. So if you do bond breaking, think about the bonding and anti-bonding. And the anti-bonding is then hopefully, if the molecule is stable, otherwise it's not stable, is an empty orbital. So you want to include those. So in general, you should have at least as many unoccupied orbitals as you have occupied which sort of go together. And since we are, in this afternoon, we're going to use point group symmetry. We run the calculation point group symmetry to save. It has for the different irreducible representations. For each occupied, you should have at least some unoccupied orbitals in that of the same irreducible representation. Well, you hopefully notice that there's sort of a bit of an inconsistency, because I talk about here looking at orbitals and deciding which ones to choose. On the other hand, I told you that I don't generate the orbitals beforehand, I do that on the fly. And there is obviously inconsistency. I mean, of course, you do an CASSCF calculation, you change your molecular orbital coefficients, but you have to start with something, otherwise you can't choose. At least in your head you have an idea of what kind of orbitals are there going to be in that molecule, because otherwise you can't choose anything. So in practice, in order to if you don't have a fixed idea already from the beginning, okay, in benzene I have 3 pi orbitals occupied, I have 3 pi orbitals virtual, so I include 6 orbitals and 6 electrons. And I can count how many electrons I have, therefore I know it's the total number of electrons divided by 2 minus the last 3 ones. So you can count which one it should be. Because you have to tell, I want to have included orbital 5, 6, and 7 in my active space. Otherwise you have to do a Hartree-Fock calculation first. And look at them and choose from there which ones to include, and then you start it again, but now tell, okay, now I want to have CASSCF and I want to have included those orbitals.